Hey everybody, this is Mr. Taylor. Well, we are finally into Unit 8. Just a couple, two or three more units, and it will be Star 2017. So, anyway, we want to begin this unit going back looking at something that we actually took a look at in the first 9 weeks. So, we want to take a look at sets and subset of numbers. Now, this is just pretty much like a recap, and the reason for it is when we leave here, we're going to start talking about square roots and estimating square roots and square roots of non perfect squares. So, we need this somewhat review, even though it's a part of this lesson, so we can understand the different type of numbers and the number sets. Well, 8.2a is the first thing we want to encounter. And 8.2a says we want to extend previous knowledge of sets and subsets using a visual representation. And we want to include, but we don't want to limit it to the different set of numbers. Counting numbers, which we say we also call natural numbers, and this is all the positive numbers that begins with 1 and it increases by increments of 1 each time. For an example, we can have the set 1, 2, 3, and so on all the way to infinity. The next set that we want to take a look at we call whole numbers. Now, whole numbers belong, or should I say, whole numbers are counting numbers. So counting numbers belong to whole numbers, but they include 0. For for an example, we have a set 0, 1, 2, 3, and so on all the way to positive infinity. Again, these numbers also begin at 0 and they increase by 1, increments of 1 each particular time. Then the next set we have are integers, and integers is the set of counting numbers, their opposite, and 0. So what that is telling us that if we have 1, we also have a negative 1, which is the opposite. If we have 2, we also have a negative 2, which is the opposite. If we have 3, we also have a negative 3, which is the opposite. And if we have infinity, we also have negative infinity. And in the middle of this, we call 0, which has no opposite. So we look at integers, and integers are characterized, or should I say denoted, by the symbol z. Then we have rational numbers. Now, rational numbers is a set of numbers that can be expressed as a fraction, a over b, or should I say a divided by b, where a and b are integers and b is not equal to 0. Reason being, if b was 0, we can't divide 0 into some number without it being undefined. So, again, rational numbers is a set of numbers that can be expressed as a fraction, a divided by b, where a and b are integers, and b is not equal to 0, which includes the subset of integers, whole numbers, and counting numbers. So all of these numbers are included in a or b with the exception of 0. Some examples are negative 3, 0, 2, negative 1 half, 11 over 7, 1 and 4 7, or 0.23 repeating. So the set of rational numbers are denoted by the symbol Q. Now, irrational numbers. These are the set of numbers that cannot be expressed as a fraction a divided by b, where a and b are integers and b is not equal to 0. We'll get to that a little bit later. Real numbers, the set of rational and irrational numbers. So the set of real numbers are denoted by the capital letter R, visual representation of a real relationship between sets and subset of numbers. And we want to just look at couple, if you don't mind. The first thing is a Venn diagram. And within the Venn diagram, you remember Venn diagram has circles, and then it shows part with another circle. Well, if we go to the rational number side, we see rational numbers, a big circle, but inside rational numbers, we have integers. Inside of integers, we have whole numbers. Inside whole numbers, we have natural and counting. So let me explain how this goes. Natural numbers are whole numbers, but they are also rational numbers. Natural numbers are also integers. Whole numbers are integers, but they're also rational. Integers are also rational, and all of these are considered real numbers. Now, the other set of numbers are irrational numbers, which is not a part of this number set at all, but they are real numbers. The next type of visual representation that we look at the subset of numbers, we call a tree diagram. So we begin with real numbers, and from real numbers, we branch off to rational numbers, and we also branch off to irrational numbers. So remember, see, nothing is coming from irrational numbers, so it means they're out there by itself. For rational, however, we have integers, and then we have non-integer rational numbers. We're talking about fractions and decimals here. Integers, we're talking about whole numbers and their opposite. And from integers, we have whole numbers, and we have whole number opposite, which means negative numbers. And from whole numbers, we have natural number or counting numbers, and we have zero. So once we are armed with this information, our purpose is to describe the relationship between sets of real numbers. So we need to be able to understand that all counting numbers are sets, or should I say subset. They belong to whole numbers, they belong to integers, they belong to rational numbers, and they belong to real numbers. They give us an example saying 2 is a counting number, but 2 is also a whole number, 2 is also an integer, 2 is rational, and 2 is real. Now let's go down to the next subset. All whole numbers are a subset of integers. They're a subset of rational numbers, and they're a subset of real numbers. Notice they're not a subset of natural numbers. So an example is 0 is a whole number, it's also an integer, it's rational, and it's real. But notice it is not a counting number. The next subset are integers. All integers are a subset of rational numbers and real numbers. Okay? Example, -2 is an integer, -2 is rational, -2 is real, but neither a whole number nor a counting number. So -2 is not whole, and -2 is not counting. Okay? All counting numbers are whole numbers and integers, and they are a subset of rational and real numbers. All natural numbers, whole numbers, and integers are a subset of rational and real numbers. Example, 4 is a counting number. It's also whole, it's also integer, it's also rational, and it's also real. But not all rational numbers are integers. Not all rational numbers are whole numbers, and not all rational numbers are real numbers. Example, 1/2 is rational, but it's not an integer. It's not whole, nor is it counting. So, terminating and repeating decimals are rational numbers, but they're not integers, they're not whole numbers, nor are they counting numbers. Example, 1.3 repeating is a repeating decimal. Therefore, it's a rational number and it's real. But we can see, because of the 0.3 repeating, it is not whole, nor is it counting. All irrational numbers now are a subset of real numbers. That's it. Let's go back and make sure you see this. All irrational numbers are a subset of real numbers, but does not belong to any of these. Okay. Example, let's see if we talk about that. Pi is a real number and it's irrational. Real numbers include all rationals, all integers, all whole, all counting, and all irrational. Not all real numbers are rational, though. Example, the square root of 2. The square root of 2 is not a rational number, but it's real. The square root of 2, therefore, must be irrational. Okay, let's move right along. 8.2b. So with 8.2b, we are asked to take a look at approximating the value of irrational numbers, including pi and the square root of numbers less than 225. And then we were asked also to locate these rational numbers on the appropriate number line. So the way we do this, we have to approximate. Now, before we get started with this approximation, everybody's sitting here looking, listening, is saying, all we got to do is take our 84, hit the blue key, x squared, my square root symbol is going to come up, and I'm going to type in the number that I'm looking for, and it's going to give me, hit enter, and it's going to give me the square root, and that's true. But let's take it a little further and see, can we look at some of these things and approximate them? And what do we mean by approximate? So when we working with 8.2b, they're asking us to approximate the value of an irrational number. Okay, so let's take a look. We just talked about what irrational numbers are. We said that they are numbers that cannot be expressed as a fraction. Rational number approximation of irrational numbers to appropriate place value for content of the mathematical and word problem situation. So in plain words, what we're going to do is we're going to find two numbers that either on the left and on the right of our approximation. We'll always use this particular symbol, which means approximation. And I think what I want to do is I want to show you something right here before we get too far. If I take a look at, let's say, the square root of 15. And if I want to approximate its value, I will look at a perfect square to the right of it, which is 16, and a perfect square to the left of it, which is 9. Well, I know that this one is going to be 4 times 4. Now, I don't want to, let's just look at it this way first. I know, of course, I do know that a negative 4 times a negative 4 is going to give you 16. But we want to look at this first. And then over here, we're talking about 3 times 3. So if I'm going to approximate where 15 is, I could easily say the square root of 15 on the number line comes between 3 and 4. So this is where we want to get to when we're looking at estimating these square roots, these irrational numbers and their square roots and placing them. So these are the things that as we go forth, I definitely want you guys to take a good look at these definitions that we have posted and how we are actually going to work the problem. Well, since I've already put that up there, let's go ahead and take a look at the problem. So remember we talked about, I just told you about this particular square root. I said, well, let's take a look at the square root of 16. And we got 4. Well, 4 is called the principal square root. It's the positive square root, the positive root of a square root. It's the positive root. But we also have what we call the opposite principal square root. We have both of these. So what I want to do is I want to let you take a look at both, and then we'll see how it applies. So if I want to approximate the value of the square root of a negative square root of 224, well, I must find a square root to the left and a square perfect square to the right. So 14 times 14 is going to give me 196. 196 is less than 224, so it must come to the left. And then 15 times 15 is 225. So 225 is more than 224, so it must be on the right. So I can say that the square root of 224 falls between a negative 14, because I'm looking for the square root of a negative 224. It falls between a negative 14 and a negative 15. Since 224 is closer than 225 than 196, then a negative square root of 224 is closer to the square root of a negative 15. So if you took your calculator to approximate, you will see that you would get a negative 14.97, which is definitely close. But we could have definitely looked at that and made that approximation. So this is when we're looking at the opposite principal root of a number. Well, what about if we're looking at the principal root of a number? Same square root of 224. So again, we're looking at 14 squared, because 14 times 14 is 196, and 15 squared because 15 times 15 is 225. And we can come to the same consensus that 14 is to the left, 15 is to the right. And because 224 is closer to 225, we can say that the square root of 224 must be something like 14.97. All right, we're moving right along. It works the same way with anything that we do. If we look at the opposite of a principal root and approximate the value, and notice we're dealing with, up here, we're dealing with non-perfect squares. So to approximate the value of 2.1, we know if we just look at without the negative, guys, we're looking at where do this 2.1 fall on the number line. Well, let's take a look. We know 1 times 1 is 1, and 2 times 2 is 4. So 2.1 falls between 1 and 2 on the number line. But remember also we have these negatives, so we're talking about a negative 1 and a negative 2. Now, think about this. What is it closer to? Is it closer to 2, which means is it closer to 4, or is it closer to 1? It's almost in the middle. But if we use the calculator, again, how do we use this calculator? Well, we just do second key and second, and then we do the square root key. No, that's not right. We'll do, let's get this out of the way. We'll do second x squared, which is going to yield us the square root key, and then underneath we'll put 2.1. Or we can put the opposite of 2.1. So this is how we generate these if we're going to use a calculator. But again, just a good guess and check. So whatever you do, say if I thought, well, maybe the square root of 2.1 Maybe, man, I can put a question mark. Maybe it's 3. Well, you can always check because the opposite of finding the square root is to square the number. So if I do 3 squared or 3 times 3, I'm going to get 9. So we can all, please feel free. Please, you must check if you're going to go through and use this approximation. Okay. So what I want to do is before we move on any bitty further, let's just go ahead and stop here, and then we'll take up the next time looking at fractions and finding the square root of fractions. Works the same way. You just take the top and the bottom and find the square root. All right, this is Mr. Taylor. Didn't mean to take up all your time, but I'll see you soon.